and inverse elements and this kind of counting, and there could be very much relations to that what was shown last weekend. But I had unfortunately not the time yet to have a look on the video recording. I will do that once I have time. Okay. And to say that I prepared today would be an understatement. So I just overflow over the announcement of you, Rajan. And honestly, I'm not completely sure I will understand what's up to this today. So I'll try my best to follow you.
No, it's just a new thing. Yeah, no problem. It's a new thing. I'll just say it. It's already on. So essentially, this is an attempt. One of the things is I found my formalism S2 formalism, but going from S, there is no direct path. People for the group,
and I might not be able to stay in the Q&A to put this. I have only about 2 hours, maybe a little more, but around 2 hours.
Okay, I think we'll probably we might even stop it before then, but two max.
Finish.
Also, Rajan, there is a slight problem with your mic. Your sound doesn't. So
let me
definitely need to fix that.
I think last time you switched to the microphone of your PC, which was giving better results than your headset.
Now, is it still a problem? Can you hear?
It's a little bit low noise, but we hear now.
Problem of hearing?
No more interruptions from this point of view.
Okay. Is it okay?
Yeah, it seems to be good, yeah. Okay. Do you want to start again, Rajan?
Okay.
Just kick it off. Yeah.
Okay. So okay.
Oh, lovely. Yeah.
So I'll go slide.
No, there is a problem there, I think. Okay, we'll just try it out there, and if there's a problem
of hearing,
yeah, I'll let you know in the first 5 minutes or something.
Okay. Okay. So this is an attempt to convert the S2 quaternion group to S4 crystal groups, because that's important. What we developed formalism, the S2 group has a lot of advantages. You can see that, I have more than 30 papers, peer-reviewed papers, that goes into detail and understand and even connect to the colloquial space, things like that. But that's S2 group is a it's a commutative abelian group. But when you go from S2 to S3, the S3 and anything greater than S2 is non-commutative. So that's a big problem. So people can come from S group or SU group, and then Christopher has done a lot with S4. That's why I feel that there may be a connection we can make eventually. But eventually, we want to do the SU group, which is the main group for the particle physics and also the standard model, things like that. So you have to get to that to be able to connect with that. That's what we want to do. I started with the, so let me briefly mention here, Davis Rajan Iyer, all of you know on this, and I am presenting at this TechNet Earth Global Symposia that we hope, will resolve some of the problems of grand unified physics. And, I try to finish it in about half an hour to 45 minutes, and then we'll go on to question and answers, discussion, debates. So let me mention that this is just an attempt. So we need a lot of clarification. Many of the things may not be understandable. Why I did that. So we'll, do it as much possible today to go into discussion. Maybe later on next week and subsequent weeks, we can do more clarification, because the next step is to connect with Christopher's crystal geometry. So, I think that's a huge step. I mean, the steps that I luckily, and I feel good that I'm able to do something. I was not sure whether I can do something. So the problem solving is how to convert the S2 group to S4 group. That's a huge problem. I went through some of the literature. I couldn't do all of them, but I think I went to some critical literature, and there is no way they describe, about the connection between S2, S3, and S4, but there is no way to go from S2 to S4. You can go the other way. So this is like climbing, against the tide or like a mountain. But I think I found a technique with the thing. It gave me an idea, and I was emailing with the Martin Hay, sorry, about his chiral kind thing, about the new thing, and what I am presenting is a little bit of that. A little bit after the discussion, I could extend this one. It's an application. It's not a direct connection to his logic, which is highly complex, and we're still trying to understand what it is. But I could use that. He analyzed for me what I had, and he said that, yeah, that I understand how the connection between S2, S4, and his thing to some degree, and that's sufficient to do the physics, I think. So what I started here is a review of what we have done. I like to do this because I think this is still a something that people are not completely sure about, and I can understand that because it's a whole new answers thing, and I have presented in conferences, things like that, and some of the mathematicians, they could ask questions, very relevant questions, I should say. Recently I presented in the Istanbul World Conference, and there were a couple of mathematicians who asked excellent questions about the physics, about space field, things like that. That allowed me to go further. So we started with Emmanuel Margulis's work. I worked with him because he's doing magneton experiments, and he presented very nicely about his PhD thesis on electron, the new electron structure that he has come up with. So essentially, I and he are, I met him in Greeks, and then we started off doing many things, very difficult things. So these are very difficult to solve problems. Let me emphasize that. But we have made some headway in this one, and there's a lot more to do. That's the idea of phase 2. Phase 1 was to come up, do this formalism, starting with the Helmholtz. It's essentially a Helmholtz decomposed point field theorem, you can say. So essentially, what we are showing here is the rotational field. Any field, especially point field, we convert into a rotational field, like a vortex field, and a gradient field. That's a simple thing that it starts from. But of course, you can have, if it is a rotational, you can go clockwise, anti-clockwise. So there is a parity involved, and gradient also, you can go up or down, things like that. So there is a parity involved. That's why I now say it's a space parity field. Space parity. So that's a S2 type matrix, and I show in other paper, couple of papers, that how to gauge it to string matrix, which shows the diagonal matrix shows the charge, the charge aspects or the fermion aspects, and the cross diagonal shows the mass aspect, like the Higgs mass factor. The cross diagonal is like fermionic gauge, and I develop myself, and then I publish along with Manuel, who has, he does a lot of astrophysics. So we do it together to understand about Einstein relativity and things like that, how to use them for astrophysics. So this is a fundamental math, and at some point I can describe that. It's so fundamental math that that's a new thing that connects between the inner product, outer product, and a special function. Again, this is going against the grain, so to say, and people are, even the mathematics, it's not there, but I have proved there, I derived there how to do that, and that helps to do this gauging of this field to the charge flow. So G is a gauge coupling field that's derived and then it connects with the field. So that's a whole new thing. That's a few papers that is dealing with that. Okay, so jumping on to the next one, we can transform it. Again, that's a huge thing. That's like 20-page derivation here. The transform connects the space field to the rotational field. The rotations are, there are three rotations possible: spin, we know it, the rotation of the whole thing, and also revolution. So this is a three-dimensional rotation along different axes, and so that is a fundamental thing, and that's a function of time, and then it connects to the space field. So there are a lot of, you can see there are a lot of I'm not going to details here because that's a huge thing by itself. Lagrange, all the new type of transforms, we essentially Lagrangian is used in the relativity, Hamiltonian is used in the quantum mechanics, but this Legendre is not used, but it's a very useful thing, space and time. Fourier, that we all know, between frequency and the time domain conversions. And so these are, and also Laplace. Laplace helps the flow, the mass flow, things like that. So with these, I could eliminate all the constants, and then it's a great presentation by all of Gerd, Christopher, Christian, and John, and and all the others who have participated, and Emmanuel especially. That the fundamental problem is one of the change of the constants. Even the most fundamental fine structured constant could be changing in time. And then Massa, also Corrado, also has a nice formulation of how that changes. So I know that I have to eliminate that, as well as the mass. The mass problem is a huge problem that is still unsolved, and also charge. So all these are variables that we cannot measure in the outer space. We cannot go in there and then put a probe, and this. From here we can, by using different some of it. So it's actually, so I converted all that, removed all that, and just express in terms of the space field. So that is the big thing, because that has not been done, and that proves that the universe may be like a black box. We can pull out some variables to understand mass limitation. And I briefly want to mention, and later on we can talk about, for example, in a large conference that we are planning in Hawaii, or the World Conference, that the essentially you can see why, a brief, this is just a clue or a hint, why there is so much disparity between quantum mechanics and the relativity. And the and there is that catastrophe problem, ultraviolet vacuum. And one of the main thing is that what quantum mechanics is talking about versus relativity is that relativity, the gating Einstein thing is about tensor aspects, the tensor field essentially. But the important thing about quantum relativity is that we can only figure out order of magnitude, and that is, I think we can discuss later on. So order of magnitude, I have found that so these are the two different sides of the problem. So that's where the disparity comes in. That's like a hint or clue, and I think these all these, if you put them together, I think will prove that why it is so. So that's why we can never figure out all the constants completely, very accurately. Also, it's a black box, so we are trying to get the information and trying to process it. So it's an information processing thing. So this is a huge thing, huge step here, and just putting the equations here. And then you can do inverse transform and pull out the time. Time, the whole new thing about the time is that time is a tensor, it's a rank 4 tensor, and it forms the 4 vector matrix. So that's a huge thing. And that time, when you pull out, you can express that in terms of the space field. So what happens is that interpretation, I have a couple of like 3-4 papers in the Canadian Journal of Pure and Applied Sciences, and They describe that, and then 2 of them are already published, and 2 of them are already approved for October publication. Essentially, that's almost done. I have already put the 2 papers in the ResearchGate, and all of them probably one of the interpretations, and that's a huge thing, is that in quantum level, the time is inside, and what is outside is the space field. So only space field, the time is only implicit there, but the events are what we talk about, like quantum tunneling, things like that are there. We can pull out. Mesoscopic level, both are there. And I believe that the mesoscopic level is more like S2 type thing, because S2 has a commutative abelian property, and that's very useful. Again, we need to discuss a lot more to understand what that is. All right, this is just an idea that that comes from these conjectures, and then eventually we converted. I think all of us participated with Gerd, Christian, Christopher, all of us participated, because the big problem was to convert to something that we can be computer simulated, and we converted that. And I mentioned that in one of the earlier presentations, that we can convert to the numerical matrix, but here you have permutation aspects, and then Christopher already programmed, and we have results. I'm not going to show that here, but we have results that show that it's like a diffraction symmetric pattern of a crystal type thing. So, and then we can manipulate that to get the next level. So the main idea, that is the part of the phase 2 initial program that we are starting the project, and it's a long way to go. So the first step is transforming the 2x2 S2 logistic group to 3x2 S3 logistic group. So this is partly, as we say, we had a session with Martin, and I had some email communication and some discussions previously, that essentially it's not a Boolean type of thing. It's not, just true or false. The logistics group help, because we are trying the truth of it's like an extended truth table, trying to find the truth of things that as we go, then convert it to our variables. So this truth table, extended truth table, talks about the false true, but also not false, not necessarily equal to true. And not true doesn't automatically mean false. So we keep it separately, but at many places we can collapse to binary anytime by equate. When you have a abelian or symmetric thing, you might eventually collapse to true and false. The important thing I pulled out, and what we know is from the literature, is that S4 group has 4 isomorphic subgroups of S3, and then 9 isomorphic subgroups of S2. So we can utilize this knowledge to convert it. So first I convert the S2 group. So all the S2 is collapsed into the S3 group. So we need to create a 3x3 matrix of the 2x2 matrices. So we start expanding the matrix, and that constitutes what I call the S3 logistic group. And then each one points to a different cell category. It's a categorization that here it might involve a particular, let's say a particle electron has half spin, and we have possible spins are half, 1, things like that. So, and also we can go up to 2 for graviton. We can have a spin of 2, but of course graviton is not proved yet, but it's a hypothetical particle. But in any case, so the true force will say whether, if we are choosing half and we are choosing electron, whether that's true or not. So if it is true, then it will collapse that and then put that value of the spin there. And then F2 could be for a charge, things like that. So each particle can be characterized by the row, one row, which the 4 property characterization of a particle. The next row will go to the next particle. It could be electron here, or a fermion here, a boson, or electron, let me go back one more step. Things like that. So that's the idea. So that's what I'm putting it here. Convert this S3 logistic group to S4 logistic group to talk about the particles. Talk about the particle in S3 group. There are some available, but I think in order to get to the standard model particles, we have to go to the S4 isomorphic. So if you use that, you have 36 of them here. So 9 times 4, you have 36 of them of the 2x2 matrix. So then we can convert to what I call the use the spinors and also, so this becomes the coefficient of the spinor coefficient matrix, and then we have to have a spinor to convert to quantum variables. So this is the idea. It's a whole new thing, very similar thing to poly matrices, but it's an extension of that. So you have now the huge matrix here of 36 elements, and then you conflate that, or vector multiply with the spinor group. And I will go to what the spinor group will consist of. The spinor group will consist of the field aspects, field and the switching aspects. So I think I go to the next slide. I show that. So this S4 logistic group to point field physics. So I apply our the theorem of I earmarked original formalism of the Helmholtz theorem. Essentially, these are EG means the gradient, and this is the clockwise rotation field, and also the space field of each of them. So the spinors have the gradient of vortex fields in them, and then we have the charge, but you have to use the parity because the charge can't have plus or minus. The same way with spin, you have spin plus or minus. And then I introduced one more thing called switch. The switch is such a thing that there are 3 modes of switches possible. And I have done some fundamental calculation. It's interesting calculation that connects with poly matrix also. That I may not have enough time to go through that today, but I'll briefly mention that. But a switch is essentially says that the switch mode is 0, means there is nothing there, it's just a vacuum, right? If it is off, the particle is there, but the particle is not active, it's passive. Where it's on means that particle is active, like electron may not be active in all the phases. We now think there are 3 phases. There's a superluminar phase, there's a subluminar space, and also the luminar space that I'm working with Emmanuel about the multi-phase systems. And there's reason to believe all the 3 phases are there. So when I multiply this coefficient matrix, which consists of these the field, all the field aspects, to the conflate with the essentially these are the charge, the 6 parameters of charge with parity. So here is the charge of one parity, charge of another parity. Then you have spin of one parity, spin of the other parity. Then you have the switch of one parity and the other parity. Okay. So that when you multiply, you get the quantum parameters, very similar to the local and global quantum parameters that so it's an extension of that. You see that these are quantum of parity 1 of the charge, of the parity 1 and 2 of the charge, the spin of quantum of the parity 1 and 2, and the switch parity of the 1 and 2 quantum variables. So I think this will describe the whole thing. Hello, Carabio, manifold, things like that. That's an extensive thing. But I think my thought processes say that it's possible to do that. But there's a long things to go on with that. So I'm basically only presenting here that this itself is, I'm sure that there are a lot of questions. Not everything may be clear because such a new thing needs a lot of clarification. And we have to dissect this one and also diagnose whether all of them are completely true or false. So this is kind of like a hypothesis in a sense, hypothetical conjecture, so to say. But I believe that we can solve that. So I mentioned here it resembles the Pauli and Dirac matrices because we can do the same thing. I was trying to do something else with the from 2 by 2, use the dimensions, go up to 5 by 5, but I find that that doesn't get to us to the particle physics or the standard model or what we can measure observable. So that's why I had to use this technique. So these are all quaternions. As we see that they contain both real and if you go to the paper, both real and imaginary components of the field. For each of them, there is real and imaginary constraints, especially the switching fields that I briefly will tell the next one has both the real and imaginary. So there are a lot of interesting, but what I'm saying that this has about 36 possible particles. You can characterize that, but not all of them are useful. And as we go along, some of them have, if you filling in this matrix, we cannot avoid that. And they may start looking like a relativistic matrix or quantum matrix, which has zeros in them. So, and then we can compare that. So we may be able to connect with that. So this matrix that has a charge, spin, and switch states with parity will characterize the correct value, can characterize the correct value of charge, spin, and switch states. And that provides understanding of all the four things along, like the gravitational, electromagnetic, strong nuclear, weak nuclear, all these fields that we know of. Also the dark matter and dark energy. So you can incorporate all that, because let's say we do the each particle. This 36 is for, actually I re-emphasize, actually all those 36 particle characterizable. Eventually we use this to characterize just one particle itself. We can do that. I think that maybe it's quite useful to do that. So let me get this pointer up there. It went out. Okay. So I don't know whether, I think you can see it. Okay, when I am pointing. All right. So just one particle, we can use this 36 by using the field. So we can look at 36 possible, or we can look at the fields, the different possibility of fields of each particle. So I can say one of them will describe the gravitational, one of them will describe the electromagnetic aspect, the strong nuclear. I mean, these two always, we have to use. There are 1, 2, 3, 4, 5, 6 of them. So 6 rows. So for example, gravitation, we use this first row for a particle, and electromagnetic, we use the second row, strong nuclear third row, weak nuclear fourth row, dark matter fifth row, and the dark energy as the sixth row. What this may show is that whether each particle electron can its exist as electromagnetic, the electromagnetic phase or field, or strong nuclear, does it have that strong nuclear? It may not have. So in that case, it becomes 0. Wherever it's not possible, it becomes 0. Weak nuclear, yeah, electron definitely can do weak nuclear, so that will be present. So that row will be positive integers, numbers, non-zero numbers. Dark matter, can it exist in the dark matter phase? We don't know yet, but I think we but so that's a questionable thing. And dark energy phase. So they have partners in there. And I briefly went through at some point, we all know, you know better than me about the standard particles like quarks, leptons, bosons. And so we have fermion, boson, quarks, leptons, hypothetical particle like graviton is still a hypothetical particle. They are not detected that yet. Superparticles, again, those are all now in the stage of hypothesis. Hadrons, baryons, and mesons. Some of them have been detected by the LHC and other hadron colliders and other particle physics measurements. So precision with the gauge field of charge, spin, switch state, parity, time, and space, I think we can describe a particle more completely with these characterizations. So this 36 group, 36, 6 by 6, will describe for each particle, like and it will describe the fields as well as the charge, spin. So that's more complete description, because we know that they can, the fermions, depending on and different forms. So it's raise the characterizing standard board particles, and Christopher has already done a lot of the crystal. We went crystal geometry. He has connected his cell groups, 24 and 120 cell group, to all these known particles, both and he's able to pull out the values. He solved. I think we can combine with that at some point and then convert this, because now there is a way to connect with the higher Markowitz formalism to that. So again, literature, I think I'm showing the extensive literature. I have briefly listed some of the literature that I went through, not all of them, so essentially, so that's a literature, group that have, yeah, excuse me for a minute. Yeah, so essentially, okay, so the charge and switch and parity, quantum matrix helps in the, sorry for the interruption there. There is some other, but in any case, let me continue here. There's, we can always whatever we missed here, but they can eventually hold key to the granulified physics of the symmetry cube, because we can property characterization here. For example, we can say fermion have a positive charge plus or minus half spin, whether it's there or not. So on-off switches states will help to figure out whether the particle can exist in that location. For example, the crystal group, things like that. Whether each particle can exist. And boson similarly, we know even less. Again, it is a very strange aspect that Emmanuel also pointed out. There is a connection between the Horn torus, which connects with the electron with the magnetron spin. So the question is a charged particle, or fundamentally it's a magnetic field aspect? That's still something we have to resolve. But using these and connecting like photons are plus or minus spin states, gravitons. So these are well known. Gravitons we don't know, but we think it's plus or minus spin states. These are what we know now. So we can come up with this theoretical simulation and then connect with what we know from particle physics measurements. And then when we correlate that, we'll see how they correlate, first of all. So verify this model. I'll also then extend the, once we know that, then we can extend this what the theory usually helps is to extend our knowledge of the observations down other property characteristics. Once we verify that within the 4 sigma level, things like that, like the Higgs boson, we can move on. Of course, as we move on, we have to keep checking because a lot of things may fall out. So that's a trial and error process we have to go through between the experiment and the theory. Of course, so finally, the theory has to be verified by the experiment. The experiment is the final say, and that will take a long time. But we can do a lot by the theory because we can eliminate a lot of things. We can say that this is not possible, this is possible, things like that. So that helps to reduce number of experiments we have to do. So critical experimental design we can come up with, which will which is reduces the amount of money that's available for that. Already at LHC, a lot of funding is done for that, but there is a limit to what we can find out. And also some of them, like superluminous thing, may be a theoretical thing. We can only understand it when it comes out of the superluminous phase into the luminous phase, and also our subluminous phase. So like I said, it's like a black box. So that's a fundamental thing that the transforms are brought about. So the expectation based on that charge gauge field, at the quantum level, is essentially a space field, like I mentioned, and the tensor time, is essentially like a vortex that starts to occur in the mesoscopic level. The Swiss states a gradient band of vortex space and time. So essentially, the on-off switches has all these stuff: gradient, vortex, and the gauge. So by using these things, we can use like an elimination method to figure out each of them. So that's a huge sorting out things. We can utilize that, and we expect the parity, like a sense that gives the field to space and time. So I believe that from these, what I could infer or intuitively kind of insight into that is that the sense is, we say the Higgs mechanism that gives the field the mass effect to get the Higgs boson, things like that. But what I'm saying is I go a step back and say, what gives the field effect? The sense is the one that gives field effect to space and time. So the sense is going to determine whether you want to give the field effect to space or time. So for example, in the gradient level, in the quantum level, it gives the sense, the field only to space as a passive thing that marks the events, and essentially that's because the time reversal is possible at the quantum level. I believe that because of quantum tunneling, things that time does not have a particular defined field because it can go back and forth because of the tunneling aspects. But when it comes to mesoscopic, both sense gives field effect to both space and time, and we see that at our level. But when you go to, again, astrophysics level, only in the space level, in the space field, it's giving. Again, the time is tucked away inside, transforms, and essentially, that's why Columbia or space and all those things come into picture, and high level topologies come into picture. And then same thing with the quantum level. So I believe that the astrophysical level, the space field can actually short circuit or it can directly communicate with the quantum level. So there is a direct correlation. That's why the information can, at the astrophysics, can go into the quantum level. There's a short circuit part like a wormhole or something that can connect to the quantum level. But we get the information only when it manifests in both space and time. So that's why there is a delay in getting the information, both quantum information as well as astrophysics level. What's going on, we know only after a while. It could, it could be even billions of years before we know it. astrophysics level. In any case, quaternion, I have described the 6 different parameters, spinor parameters, and the quantum 6 based on the charge, spin, and the switching states. With the parity, it gives the 6 quantitatively for each S4 group particle. So it's X of the quantum local, and you can see that the 2 of them here goes into the 6 of the quantum particles. So the quantum characterizations, the S2 group. S2 group has a good thing that it can connect with the local and global, but it's only a general commutative relationship, the overall quantum level information. But now we go into dissect more into details, and we get these 6 parameters, which are quite important because that's how a particle is characterized. So the switching states are, again, this is the derivation I was talking about with Pauli matrices. When I did that, I can connect between the off and on. So very important because we have to convert this thing into a digital thing, that off and on, they don't have numbers per se. So we have to find a relationship, and this is a complex relationship, which I believe is a quaternion, I minus thing. So it has both imaginary and real aspects, and I can now describe off in terms of on. So if it is 1 here, on, normally we take it as 1 in the digital physics, on equal to 1, then the off can be calculated by using, I have found a way to figure out on off what that is, and eventually in another time I'll show you we can figure out a square wave, how the square wave it connects to a square wave. Again, I'm not going to go into details of that, but essentially want to say that each point can be in a state of on, off, or 0. So 0 switch state means particle is not there. So it's just vacuum, there is no particle there. So that's a very important point. And on-off means the particle is there, but it's not participating. Like in dark matter, for example, it's there, but it's not participating, right? Somehow. And then on state in our, subluminal level, the particle comes on, like electron, things like that. So when I did this calculation, specifically for S2 group, I could show that it performs. I converted digital to analog by some technique. Worm forms like multipliers, laser technique. So we can describe the photomultipliers and also lasers based on this formulation, which connects the numeration matrix with the Pauli matrices. We know there are 3 Pauli matrices possible, but we have to use the quaternion value of the Pauli matrices. That's about what I want to say. Matrix having the parity of charge, spin, and switching states. Again, I'm going to pull out that these are the 6 variables I talked about. And again, characterizes, I'm just repeating that, essentially characterizes the charge of different sites. The resultant quantum property, so this is of them, gives about the charge, spin, and switch states with the parity. So these characterizes. So that is the main thing here. So this characterization of the quantum, very similar to the Bohr, you have principal quantum number, things like that, the 3 quantum numbers of the Bohr characterization of the electron as well as of the atoms. So we can connect with that with these, because it has an additional switch states, 2 more states we can put in, and that helps to understand more about what's going on. So in summary, I just want to say that we just reviewed the physics formalism, just the equations I put, and also about a rank 4 vector and the space parity fields, and essentially converted to a numeration matrix that can be computer simulated. That Christopher already did that, and we have the results. Then the transformation of S2 logistic group use the logistics aspects to convert from S2 to S3. So that's a new thing here. And that then helped to figure out about the S4 quaternion matrix and the spinor matrix that describes the and that gets the quantum parametric matrix that describes the parity of charge or spin and switch state to conflate the coefficient matrix, which consists of all the field aspects. Certain generators quantify particle physics, can connect. Now we can correlate with particle physics and see how they match with the S4 group, and also the crystal geometry that Christopher was talking about. And so we can extend this one, the QG and QL description of the S2 group, and essentially the Pauli and Dirac matrices of the charge and spin states are extended with additional aspect of the switch states and with the parity. The parity is already considered, but CPT is still a problem. Charge parity, time reversal. I think with the switch states, we may be able to solve that. That's my feeling about that. So these are just the references. I have a lot of references. The papers that I published, a brief list of the papers. These are peer-reviewed papers mostly, and also presentations in some other conferences. And then I have also here more recent ones. This is a proof formalism talked about. I worked with, I did that and then published along with manual. It's a new thing that gauges, that helps in gauging to the higher level. And then astrophysics did that, and then all six of us, Manuel, Christopher, John, Menzong, and Emily Taylor, I think in the Canadian community that shows a lot of problem solving there. And then theoretical to experimental, we had to eventually solve the observables. We had to pull out that's another paper, recent paper. Then these are the papers I was talking about: the strong gravity, the weak gravity. It's already published in the CJ Pass, and also this is one going be published in October, and Sakarango already he's excellent editor who has done a good job of corrections for some of the things, because he has worked on it, Sakaranga waves, things like that. So he knows about these things to the extent that is necessary. But these are new things. Again, another one about the hot PDP circuit mechanism that I have been talking about. Deviates the particle from the superluminar phase. Then this is the algorithm, how the transforms, how to connect with the graphics, with the simulation that Christopher did. It shows here. These are all derivation. These are all results of the derivation. Again, it's a 20-page derivation, so I have not shown it anywhere. At one point, I can show that, and observers, and I connect to Sabina's work, as well as some literature aspects. When I inquired about how to convert a S4 group, there are only very few things available there. And whether it's commutative, people have proved some of the things here. Why the S2 group is abelian, SO2 group, things like that. People have proved some more things, and then these are handled about the power of empty space, so understand more about the vacuum. Then I have put only Wikipedia right now, but I think you can eventually look into these particular quarks and leptons or fermions. We know that Pauli matrices, but many of them are already known. Pauli Dirac matrices. Parity physics itself is a big thing, big topic. And then second order, why graviton is a second order tensor boson shows that. Then mediation of the spin charge particle, fermion, boson, lepton, hypothetical particle, partner particle, composite particles like hadrons, baryons, mesons. These are all there. And there, in that list of particles, it's a list of particles there. They also describe magnetic monopole. That is and is predicted by some granulified theories. Okay, so the group theory, some of the group theory can be found on application to quantum mechanics. Then the symplectic groups and the KD table that I think Christopher uses a lot is also available, and that's an extensive thing. So thank you very much. I think that's a brief presentation. So I'd like to welcome you to ask questions, and I know there will be plenty. Can only resolve some of it, and you know what I have talked about. You may be understand. You probably I was able to communicate. I would generally say it's anywhere from 10 to 50%, because I didn't expect all of them to be understandable without a lot of things going on, and diagonizing them, dissecting them. That Christopher and also Christian does it so wonderfully with their schemes, which are extensive evaluatory schemes. We can go through it later. So thank you very much for listening. So if you have questions, I'll welcome that.
Thank you, Rajan.
So okay.
Yeah, sorry, I was muted. Yeah, thanks,
no problem.
Rajan. That was great.
Thank you.
I have a few questions. So S2, you're saying is quaternion group, and then you were saying it was. Did you say at the start it was non-commutative? Because
S2 is a commutative. S2 will be commutative.
Right, but the quaternions are non-commutative, aren't they?
With the quaternions, they are. So that's a good point. That's a good point, because sorry. Let me go back there. I don't know what happened there, but
yeah, it'd be good to have the slides as a reference, all right?
Yeah, something it went off, so I had to go back there again. I think I may have to share it again.
Yeah, a different tab or something.
So it actually went into something.
Okay.
Oh, it actually switched off that one. Okay. Again. Okay. So let me access it again. Let me access the. I think this is the one. Okay. So now I can. Can now present it again, share the screen. Okay, hopefully that will come. Okay. Is it there? Let me check.
Yeah.
Cannot check. All right. So essentially, yeah. So let me. But I had to. I'm not able to see, so I'm trying to figure out. Share the screen to the. Okay, I think. And then go to slide. So now I think I can. Yeah. Since it is. I can work with this one. So let's go.
You seem to be cutting out a lot more, Rajan.
No.
wire connection or something.
How about now? Is it better?
Yeah, that's better.
No?
Yep.
Oh, okay.
So yeah, so the
So I'm
question,
trying to
I don't know
move
if
this
you want
one.
to repeat the question, or are you on top of it?
Yeah, I got stuck somehow. Luckily, it didn't get stuck when I was presenting. I was afraid of that. But we go back to that there. Stop share that again. Let me.
Rajan, your microphone is, from my point of view, distorted.
Okay, the mic problem.
Yeah, it's cutting out again. Yeah, if you have your problem with the slides and you're presenting them, sometimes you can go back out to the normal view and just click on the slide and go in, do it manually, like instead of clicking through them if that's not working for some reason.
So let me again go back and see which mic will do a better job. Is it any? Are you able to hear better? No.
Yeah, it's
not at all.
Maybe it's like when you're
about
moving
now? How about
yeah.
How about now? Is it good?
Seems pretty good. Yeah. Okay.
There are two of them, I think. Which one is better? This one better or the previous one?
Was the previous one just a few seconds ago?
This one seems to be
good.
better.
Yeah.
Okay.
So
let me. I think I can share the screen now. We try again. Hopefully this will work this time. So yeah, I think I think this is working now. All right.
So if you go out of presenter mode there, Raja.
So
full screen. If you go out of the presenting.
Yeah. So this is now. Yeah, I'm trying to move it now. Let me see whether it moves. Slideshow. Okay. I think it'll. So let me try going there.
Oh, there you go.
Can you see now?
Yeah.
I think it's moving. It's moving. Yeah, it's moving now.
Right. It's working now.
Talking about this S2 group, right? You had a question about the S2 group. This S2 group here is actually abelian. I mentioned here the S2 group, when I did the literature survey, the 4 elements, abelian quaternion commutative group. So most of the S2, not all of them are commutative. It's a very important thing, but I think they have the abelian property. Now, the question becomes quaternion. Like it becomes like the imaginary value. Suppose this has imaginary value, they won't be commutative. If it's a real value, the 2x2 matrix essentially is a commutative or abelian group, which means that we can, the inverse and the forward and the inverse transforms, they all match together, and it has nice property, and this nice property is the one that helps for the S2, whereas this nice property is not there for S3 or S4 group. So we are limited. We can only go one way. The order of matrix matters, which means if we interchange the matrix, they don't have the same property. So the parity becomes a problem. You see that? The parity is one of the things that get affected. And that's why the parity is part of the problem. The CPT problem, parity is one of the problems. And there are a lot of people like Bender and a lot of other people. Carl Bender extensively looked into the parity aspects. And there are a lot of papers he has published, and he's one of the trendsetters in that. And also Catherine Jones, people like that. They worked on the parity aspects, and that's a big problem. My plus or minus one, then what happens when they become imaginary? They did all the way to Fourier sheet analysis, things like that. It's a very extensive mathematical technique they have used. So that's a huge problem. So that's what we wanted to avoid here. Try to keep it commutative, because a commutative has a lot of properties to figure out. It cannot be done in S4 group. A lot of things, the analysis that we did, we cannot do the S4 group. Even the extended, I think the previous one I talked, this one, for example, this extended, so are you able to see my, okay. I think you can see the screen. So this extended thing you can do in the X2 group, we cannot do this in the S4 group. So we have to come back to S2 to understand these kinds of things. And the same way here also, this transform again, for even the time, pulling out the time and understand the time, how the sense give the field to time and space, we cannot do in S4. And even this calculation, we can, when you go to S4, that's what I am showing. We have these extended spinors. When you go here, so this is the essential result of that. So you have these 6 spinors separately, and this is a complex matrix. S2 is a very simple matrix, so we can manipulate quite a lot. S4 is more complex matrix. Is quite quite low. So we have to work with that. Oftentimes, that's what I'm saying. It's a nice seamless transition between S2 and S4 will help to figure out. So we figure out these values and then go back to S2 again to find out more about the field and everything. Come back again here. So we have to seamlessly transfer between S2 and S4 to really understand what's going on and solve the problem of this parity and things like that. With that, I think we can solve that. That's one of the advantages of this one. Yeah. So does that answer part of your question, Christopher, or you need more clarification?
Yeah, no, I think I think you answered it. I'm not entirely sure I fully understand, but I accept your answer. Let's put it that way.
Yeah,
so,
essentially, what I'm saying.
Anyway.
Yeah.
I think it's just if you're saying S2 is abelian and that it's, what is it, isomorphic with the quaternion?
Yeah, to S4. Yeah, it can be made to isomorphic to S4, and we need this.
No. With the quaternions, I said with the quaternions, it wouldn't be isomorphic with S4. It would be automorphic, or it would be an automorphism.
Yeah. So those are the details we have to go into. The quaternion will create problem. So
I think it's a bit strange if it's by the sense of it, S2, it has 4 elements. Yeah. So it's isomorphic with the quaternions.
Yeah.
Or is it have you found proof that is directly isomorphic with the quaternions?
Quaternion aspect does complicate things. But
are they? It should say in the literature whether they're isomorphic. I mean, they're probably 2 of the simplest groups that exist.
Yeah. See, for example, you have polymatrices, right? One of them is just matrices, but essentially, let me go here. But the polymatrix essentially is like 0, 0.
The quaternions are isomorphic with the poly matrices. Yeah. They are the same thing.
You have the polymatrices. Yeah.
But the question is about S2. The question is about S2. Like, go ahead.
Yeah.
Are you saying that S2 is
so, for example, the polymatrix, one of the polymatrix is, this is 0, 0 here, and then it will be -1, I think it's 1 here, something like that. That's nicely abelian commutative, right? But when there's another polymatrix which shows 0, 0, -I plus I, right? That's another polymatrix, and that is that connects to quaternion thing. But I think they are still commutative.
No, they're not. No.
Yeah, that's the problem. Yeah, that's what I thought.
polymatrix,
They're not. That's what
right.
I thought.
Yeah. I mean, you were looking into whether some matrices can be commutative. Is that it?
Yeah.
As far as I know, that's the property of matrices, that they're non-commutative. So
in general, so it's more of exception. The abelian commutative group is more of an exception than the rule. You know, I agree with that. When I looked at it, that's what it is. So I mean, only the two of the.
I've never heard of that before. I mean, you obviously did some research into it. I just heard that matrices are non-commutative, so I didn't look into it anymore. Have you discovered something else? Have you discovered that they are?
Commutative means like you have something like a multiplication factor, like x or a, like a times this matrix. You can have this matrix times a. That's commutative. That's all. But if you have a matrix,
well, then that's not two matrices though. That's a matrix times a constant. But what's a constant? What's
so
a
if it's a constant matrix?
Constant times a matrix, and then a matrix times a constant. Yeah, that would probably be the same result.
Exactly.
Okay, but those aren't two matrices. So if two matrices, then that's a different scenario. Okay.
Yeah.
So so by that logic, the polymatrices aren't commutative. That's why they link to isomorphically with the quaternions, which aren't commutative. And then so it's the jury is if S2 is commutative, then it doesn't seem like they'll be isomorphic.
No, so you have to convert to quaternions to be isomorphic. So this one, for example, see if we can find the determinant. For example, it's a real value determinant, right, of a matrix. That becomes a constant in front of the, like a spinor or something. That then becomes commutative. And now you convert it back. So that's the job you have to do. We have to convert it back into the quaternion in order to become correlate with the S4 group or the quaternion. The quaternions only connect with the S2, the S4. We cannot.
Well, that's what I'm saying. It looks like they don't connect with S2.
Which one?
Because they're non-commutative.
The quaternions?
Yeah, that's what the point I'm making. It seems like how can there be connection there? If one is
like polymatrices, they are quaternions, right?
Yeah.
But they are non-commutative. They are non-commutative quaternions.
Yeah.
Isn't it?
Yeah. We went over this. Polymatrices non-commutative, quaternions non-commutative.
Yeah. But they are still S2 group.
S2 is commutative, so there can't be a link between the two. Or can there?
No. This one will connect with that. See, I convert the quaternions back into numerical matrix. So when you convert back into a numerical matrix, we can make it commutative.
No, you can't, because I don't think the matrices are non-commutative.
No. We have to find the determinant. We have to use the value of the determinant.
Oh.
So we have to convert it numerical and then find the determinant.
What is the determinant here? So then you have a constant value like 1 or 0 or -2 or whatever.
Yeah, if you have 0.
What do you do with that? I mean, I suppose then you could multiply that with the determinant of another matrix, and that would be commutative. Oh, okay. Have you done that out to show that that is accurate?
Yeah, if we
Like,
can.
well, yeah, that's interesting. Well, if you can
Seamless
do
thing
that, that might be a way of doing it. Be interesting. You'd actually have to do that out though, and show that that's the case.
Yeah.
Because at the moment, I don't see
So
that.
we will
But
do
anyway,
it in another time. Yeah, that's a good point.
yeah, well, yeah, you'd probably have to
Excellent
do
point.
that. You'd have to do that
Yeah.
first before you start. You know, you need to get the groundwork completely solid, or else, you know,
Okay.
everything you do after that's gonna just be wrong. It's
Yeah.
like if
Yeah.
everything is based off of one idea and that idea is flawed, then everything after that's going to be wrong.
Yeah, it's true. I agree with that. Yeah, that's why we diagonalize this and then dissect it and find out these are correct. But this is a step. You know, what I find is a step to connect these things together. But there's a lot of things that we, like you mentioned, about the commutative and non-commutative things. That's something we have to do more research on. I agree with that.
Yeah, well,
to
I mean,
ensure that it needs.
you know, you might not be totally wrong. You might be just. I mean, well, if you did take that step, then it would be wrong. But if you know, if there's a different meaning, maybe I'm not interpreting what you're saying correctly. So, okay, so we'll move on. There's other stuff.
References.
Well, you're talking about Helmholtz gradient vortex electromagnetism. And so well, Helmholtz gradient and the vortex, that's electromagnetism, isn't it? So then you have like a Einstein field equation for electromagnetism or something? Is that what you're doing? You're kind of using something along those lines? Is that the space field?
It's a reduced form.
Oh.
Yeah, it's a reduced form of the Einstein.
I'm not very good at, I mean, so are you suggesting that at like very small sizes, the electromagnetic field is strong enough to create or the rotations and is strong enough to create these fields? Right, okay, so that's a standard idea. Transform, right. You say how do you say Legendre transforms. You don't use that in equation 1, no?
Equation, yes. In this
this one, equation 3, sorry, it's not in there, no? I thought you were
this is a Legendre transform.
Which one? The second one.
Yeah, this. Oh. Yeah, the third one here, the small f. The small f is a Legendre.
Right.
Of the Laplacian, Legendre of the Laplacian.
All right. And so talk us through that. So the first one there, you've x equals to the Laplacian with a sort of a, or is that the Lagrangian?
The Fourier. This is a Fourier.
Right.
L is Laplacian. This is Fourier.
Okay. And then you've G, and then you've got spin. So the subscript spin is you're just talking about spin of the particle. Is that it?
Yeah, spin of the spin of the particles, the rotation.
Okay.
And the revolution.
And so you have one in cos and one in sine. So is this going back to like Euler's formula, or is it related to that? Is it just
in some ways? Yeah, the Euler's formula comes in whenever you have the imaginary part. The Euler's formula automatically comes there. That's one of the standard things.
Yeah, I think you can leave out. You can even, some people have shown you can leave out the imaginary part. But I'm just wondering, because you've cos theta, sine theta. I'm pretty well. Correct me if I'm wrong. Oh yeah, I'd have to look into that. So you're saying that it's not a circle. These are like 4 vectors in a 4 vector. Yeah. Right. So one of them is time. Is that the k revolution, or are they all? They're all time.
No. They are a function of time. They all change with time.
So you put the time into the function though, is it? Because you've got the t inside the bracket. Yeah.
They are all functions of time. The spin, everything is a function of, because in time the spin can change, right? The rotation can change, the revolution can change in time. They are all functions.
Okay, but you're putting in the time, but what is the like? Because usually you'd put in a variable into the equation, and then step forward through time, and then that would change the how. So So time is time just a number, like, and it just counts up 1, 2, and then you do the equation for each value or something?
No, time is a variable here. So
Yeah.
I'm saying the theta, which is a rotate spin, is a function of
Yeah.
time. That's all.
Oh, okay. So that's what that statement
Spin
means.
as a function.
Yeah. So what about
Yeah.
eta rotation t? What is that? That's the rotation of the entire particle,
Which
is
one?
it?
Rotation.
Or what
Yeah,
is
this is a
that?
spin. This is a rotation.
Eta?
This is
That's
eta.
similar.
This is theta. This is eta. This
Yeah,
is
sorry,
kappa.
eta. Sorry. Kappa, right. Okay, so you have the rotation. So what's the difference between rotation and revolution in this?
Okay. So that's the whole assembly. Like, for example, you take the PDP assembly, it's easier to explain, but it's true of the particles also. The particle has a spin because it's on, right? Whereas the rotation is around something else, like the electron is rotating around a nucleus.
What if it's not? What if it's
revolution
not around?
Is the whole thing.
Is if the whole thing is rotating. Yeah. Okay, interesting. So
rotating.
Yeah, so obviously if it's a particle that's not part of an atom, then those last two will be zero. Or one of them will be zero.
Yeah,
rotation.
I mean they collapse similar things, but this is a general formulation that is different for each. Like particles will collapse to probably spin, and an electron maybe have only a spin if you are just looking at electron.
Okay.
Right?
And so what are you taking the Fourier transform? You take the Fourier transform of that, and it's the inverse Fourier transform. And then what's G?
Yeah, inverse Fourier.
So
G is like a gauge function.
Right. Okay. So yeah, the whole thing is a function.
It's a differential,
and then,
first order differential, you can say.
Right. And then so you have the Fourier. Is that related to the Schrödinger equation?
Yeah, Schrödinger equation is only it's not a general form. It comes into the picture here, but this is more generalized form of Schrödinger
Why do you
equation.
need the Fourier transform there?
Fourier, because I'm connecting between the frequency and the time domain. So I had to convert this to the time domain into frequency domain. So I do the inverse transform.
Okay, fine. And then the Laplacian is just, what's that going to help you with? It's just
the flow of the matter, the
right.
field,
Okay.
the field flow.
Right. Is that the kind of, yeah. And then so we have that again. So we've gone through all of that. This time it happens to be to the power of -2. Okay.
Yeah. So this is the differential of the Laplace.
Yeah.
This is the Laplace directly, right, of the thing. So when you calculate that, it has a non-linear thing. It is not just a linear square of that, and the square aspects come into manufacture. Even I think Christian has pointed out.
That's true.
The square somewhere. So this shows that it's a derivation, but it comes automatically from the derivation. So the square aspects, I think, is kind of verifies that this derivation is okay. Because if the square doesn't come, there's a problem. That's what you can understand about the whole aspect.
So it comes from some part of however you work this out, I guess. And then, so you have a Laplacian, which is like the flow, like the path of least resistance,
the field,
kind of thing.
The path of least resistance, yeah, that's one of the.
So it's how the particle would move in the field, kind of.
Yeah.
And then you have the differential of that, which tells you what, the speed or the.
Yeah, the speed aspect. Yes, exactly.
Oh, okay. So G, and then we have the Legendre transform next.
Yeah, space and time.
Is that log? Is that a log next to it?
Yeah, natural logarithm. Yes.
Right, and then the Laplacian again. So we've gone over all of that. We know what that is, and then you've omega sub QG.
Angular
angular momentum T. Okay, and then the log. So you're taking the log there. Why are you doing that? Do you want that to be? What is that?
It's exponential function. This exponential function that we have to bring it back into the like e power x form, right? We have to do a natural logarithm to bring back to x form, and the legender here converts the time into the space domain. So we need a space. It's a conversion between space and time domain, and then you get the speed. So but the derivation finally, I mean, so good to find out what the equation is telling, but it comes out of the derivation that the space and the time are highly complex because you're the fourth power of the velocity coming into picture. So that's where the complexity is. The space and the time are not directly related. Actually, in the normal levels, if you differentiate velocity with respect to time, you get acceleration. But when you convert it, you got to the fourth power connection between time and space and all that. So that's why you have to go through this whole process, and essentially it becomes an exponential function. If you look at the time evolution, if you look at that, it's an exponential function. That's a normal thing that's used, the time evolution, but that's an exponential function.
And then you're taking the Legendre, so as the thing is going exponentially up, you're taking the tangent bundle as it crosses y.
Yeah.
Right?
A good point. Yeah, great point. Excellent point, Christopher. Yeah, so that tangent bundle, and then see, we have to get into space, right? From the speed and the time aspect into space. It's not direct. There's no linear connection. It's non-linear. That's what this one shows. I mean, when I directly non-linear, that's why we are not, the Newtonian equation, we have to reduce to that to connect to the Newtonian form of equation, or the equation of state. Very simple Galilean Newtonian thing. When you go into the quantum level or things like that, you have the fourth power, things like that coming into picture, the speed and the relationship. They're non-linear, totally non-linear, space and the time. And that's the problem. So when you get to the angular momentum, we have to reduce it back to the normal level because we have to get R here, right? Some of that R omega to get the speed, or we have to, multiply that angular momentum converted to the linear speed, right? So we need all these transformations. Cost and time are now much higher level, higher order attitude, and we have to bring it back in there. So essentially, yeah, we can interpret that equation in that way. I think it should be interpretable. I believe that any equation you look into that, just the final equation, if we diagonalize that or dissect that, it should bring out some of the key characteristics what you're talking. I agree with that. So I think, yeah, I didn't think of that much because I was deriving, but to some degree I was cross-checking whether it's correct or wrong, because the equation doesn't portray the physics you develop. I think they should be, you can consider that as a, as a problem. But I think this will, eventually we can, although the interpretation is not straightforward, easy, I think can be interpreted. And what you're talking about is a very important critical point. I agree with that.
Okay, and then so all of that, it just becomes a vector x, and we're not even a vector, it's a position, and then
then I do the
was it a gradient or something, or
it's a scalar space field. So you have to become a scalar. It's becoming a scalar. The vector form is converted to scalar form.
Okay. So yeah, okay. Like I don't understand all of that, to be honest with you, Raj.
Yeah, it's a complex.
I know more than
situations
I
are
did.
like that. We can. Yeah.
I kind of get it a bit.
We can probably take a break. If you like to take a break, 10 minutes break. You want to take 10-15 minutes break?
That sounds good. That sounds good. Yeah.
Thanks.
No problem.
Yeah, we'll come back to it. Excellent questions. Thank you, Christopher. Christian also may have questions, so we'll go over that. Thanks.
Yeah, exactly. Thank you.
Yeah, we're not easily able to ask questions because most of the math, I think, I'm not able to fully follow. So while
Okay.
I have the basics of that, what you do there, but I have probably a tough question regarding to your input values when you go to your first page. And I think we had that discussion 3 weeks ago or something, already a
Okay.
little bit pointed in. You start with matrices of Boolean values like true and false, and
Yeah,
whatever binary or non-binary values you give them. So I'm just assuming now, let's say you would arbitrary is a matter of definition. In IT, it is a matter of definition, nothing to do with physics. So let's assume for a moment you give, just for my argument to better understand an argument, so you can follow what I'm trying to ask. You would give false to 0 and true to
take
1.
a break.
And not false
Christian,
is a
10
different state
minutes.
than sorry?
Yeah, he's asking. He said we should take a 10-minute break.
Can
and
we
then,
take a 10-minute break?
Okay. Yeah, that's it.
Yeah.
Then we see
Great.
10 minutes.
And then
Thank
you can ask questions then.
Yeah, we'll
Thanks.
come back to your question. Thank you, Christian. Thank you,
Okay.
Christian. Yeah, thank you.
Okay, back.
Hello.
Hello, how's it going? So, Christian, you had a question about, it was at the start, was it? Something to do with this, oh, the on and off, not on.
I'm not sure if you would qualify it even as a question. It is a very basic thing. You start with values like true and false, and not binary inversions of this, as we had discussed a couple of weeks ago. I think even multiple times, because there were similar questions to that. So of course, in the binary logic, true is not false because only you have two values. But in information technology, you have a state know and don't know. I had recently a discussion, as just as to get you to the background, with someone in ResearchGate who published a paper about the energy you would need to release a bit, to erase a bit, so to release a state of a bit to zero. And I was thinking about that, and I said it cannot be true, because you can not ever set a bit to true or false because you haven't defined what is 1 and 0. This is a pure human definition. And when you do so, you need a second state to say the bit is known or not. That would erase the bit, but then the original bit is meaningless. And from an entropy point of view, it would need complete randomness once the bit is released. Like, think of an very old EEPROM device. You would erase it with ultraviolet light, so all its cells would become 0. But that is a physical interpretation of that, what the chip was constructed with. So this is a human artifact and has nothing to do with the physics of it. You define your values. What you cannot define is that you need another state to define that another state is valid. That is something not necessarily to do with physics, but with logic. So when you say you start with true and false, and I would just assume you could do different, so don't get my word for it, for just to better understand the questions. Assuming you would say false is 0 and true is 1 for the simplicity of to take what all others do, then a value like not false could mean two things. It could either mean, in my world, that it is anything but the defined value. So not true could be 0 because 0 is not true, but it could be also any other value you define because it is hopefully not 1. And the reverse logic for the not true would be the exact opposite of that. So when I code this with metadata, then I need only 4 bits to run that operation. So the maximum numerical value I can get in such a matrix is actually 3. So a value from 0 to 3, and then I can code your states. That doesn't mean they could be coded with other values which you have in mind, but from my informatical world where I come from, these 2 bits would be all I need. Now, here comes the question with that background in mind. Without deeper looking on the nested matrices from S2 to S3, S4, where you essentially nest your matrix in a matrix in a matrix as far as I could see from the presentation. I'm not saying that I'm understanding the Lagrangian in between, and I could partially follow that, what Christopher asked. This is just a very strange nomenclature to me, because even my physical mathematical training in high school is very long ago, and I learned it with different symbols and different, more explicit structures. But say you for the sake of yourself, like in my iSpace, I do my coding, and I give you the full credit for you have your own coding to save time on the paper, that it makes sense for you. But the question is, what will ever come out of that nested matrices when the only input values you start with is true and false? So not sure if I get that. So when you would do an exponent of 1, you get 1. When you do an exponent of 0, you get 0. When you do an integral of 1, you cannot get anything higher than 1, except you integrate from 1 to infinity. But would you do so, then they would have boundary conditions in your integrals or whatever runs your equations. So without seeing these boundary conditions or more explicit mathematical forms, my question is, what do you expect to come out when you say this and this term is a particle, this and this term might be dark matter, this and this term might be this and this? Then I understand where you want to go after. But how do you decide finally? By pure logic. I mean, do you say, you know, in iSpace, electron charge is golden ratio. So it's very simple. When you have 4 values in, I can swear there is no way you will ever get the value of golden ratio out of such a matrix, by no means, because you didn't put it in. To get it out, it would be some recursive formalism of running a rabbit style a recursion like Fibonacci or similar to get something close to that. And whatever is measured in unit systems like the SI is irrelevant because that is human artifact based. But for example, in iSpace IQ, this is not so easy anymore because these values seem to have something to do with the constants really. Now, when you look from a tensorial point, like the one which I understand you have, string theoretical style approach with matrices of matrices and tensors, I could achieve logic when you say you have this and this input conditions, and we run through that equations and hope to get the constants of nature out here. We hope to get the masses of the particles out there, whatever, and compare that to reality. But when you start with true and false and Boolean logics and even their inverses, I don't see how you get anything else than 0 and out ever, whatever you do from a mathematical operation in between. Can you enlighten me how you think you can decide a particle is an electron, or how decide a particle is a neutrino? Where do you would get its mass from when all you input in nested matrices is 0 and 1? This is what I don't understand.
You have to unmute my mic. Yeah.
Okay.
Okay. Can you hear me now? Yeah.
Now
I think I was mute. Sorry. So thank you very much, Christian. Excellent question. I don't know whether I can answer all of it because this is only a first step. There are a few steps to get to kind of thing we want to to do. Oops. Okay. All right. Let me here. Okay. So hope I don't know why it's created. Let me see. I want to see back to the slides.
I think the definition
see the slides now, right? Let me try.
Yeah, exactly.
Oh,
here
so now it's moving. Okay. Is it here? Okay. So we'll start from here. What I'm trying to do here, see, I'm using the logistics to go from, essentially the logistics allows me, this step allows me to go from S2 to S4. Then I have to convert it into the field form. So that's a big step, but this can be used. Like you mentioned, this step can be used. It can be retroactive in the sense that I can retroactively come back here, true, false. And you, like you mentioned, the binary doesn't give all the values. So you have to have something other than the binary, either than the 0 or 1, which I realized. And this one, I think, does that. So in order to use for the particle, we have to go back here. We have to go up here. So we need at least this one, which is the coefficient matrix here, right? Take electron here. The electron, does it have a rotational thing? Electron, like a spin. Spin can be considered like rotation. So in this case, and that's have a gradient. Let's say it's 0 for now. So I get the value of -12. For this, the whole matrix, the 2x2 matrix here will give a value of -12. So you can fill in that value and go to the next one. That's the charge. Let's say charge is, start with charge. So charge is -1 for electron. So you just get a value -1. So you put that numerical value, go to the next one, go to the spin. Let's say it's -half, let's say. So you get -half here. Then we go into the switch state. Let's say it is right now is on, so it's again 1. So you get what -1, -half, 1. So these are the values you get. Start with. that question, I think I go back. This is the final. Okay. So then you have the other ones, maybe 0, 0, 0, for example, to the electron. So you filled out the first one. Second one, so this is the, let's say this electromagnetic aspect. Now you go to the gravitation aspect. It's so small, you may put it as 0 or very small value. So second row may be, most of them may be 0. There may be a small value for gravitation. Then you go to strong nuclear, maybe all zeros here, for example.
Rajan, please wait a moment. When you say you may be a small value for gravitation, then for the rigidness of a paper, you have to define that. You cannot just say you might insert a value there, starting with true and false, and not give. This is not necessary to give an example. It's necessary to define things properly.
Yeah.
Of course, one can put in such a matrix measurement values. This is exactly what quantum mechanics is doing, but quantum mechanics cannot calculate any of their 21 or 23, depending how you count, values of constants of nature. They need to measure them and input them in their equations. So when you are saying you are also taking all these quantum mechanical values, which are measured and not theoretically derivable, and put them in this matrix, and you get some logic out of that matrix, whether it is dark matter in this case or not, then I might be able to follow a bit at least, then to see the direction. But I cannot see from a pure mathematic numerical part, when you start with true and false, defining 0 and 1, you need to clearly state what you put in there. I cannot, would I be a peer reviewer? I would reject the paper because I said this is undefined. You're trying to argue on something which you didn't define. Or I have not understood the method. Could also be.
Okay. Yeah, it's excellent. Like I said, this is a step. This is not the final step. It's a trial and error process. So what you mentioned is true. The second one, I say the gravitation is a small value, means that we start with that. Then we have to go through the loop. You know what I mean? You have to go through the iteration.
I don't mean understand what you mean. So low means low compared to what? Low compared to SI system definition of electric charge. Then it's low in the sense of 10 to the power of minus 42 relative to 1 for the charge, for example. But it's a matter of human definitions. How can an attempt to calculate something physically universal have a meaning with something human defined? And if so, you need to include it in the beginning on page 1, what kind of human definitions you assume before you start using that. And the only definitions I could read from my inability to follow the mathematical nomenclature you use, but that is not your problem, of course. This is just a matter with anyone. Like if I throw an iSpace paper on you, and you have never seen how programmers write, you will also have question marks in your brain. So this is not what I'm meaning. So with all credit for you having your own syntax and your own language, I know enough about quaternions and matrix of matrices because I programmed such things in the past, that they don't change your values. So when you have zeros and ones in them, all you will ever get out is zeros and ones, whatever deep you nest them. Now, when you have exponential functions, the exponential of a scalar of a diagonal of a matrix might be a value which can get higher, at least to the value of A. And when you nest it, you could get A of A or something. And then you can theoretically get different values out depending on what the logarithm and other functions in your equations do. But it is very, very difficult. You agree to go away from 0. You will nearly always be nailed on 0 when you start with a 0 somewhere. And you will have a very hard time to move away from a 1. Now, when you say 1 is, for example, stands for or minus 1 for electric charge, then you cannot say 0.00000 to the power of minus 20 will be gravitation, because that wouldn't fit in the same sentence. That has just nothing to do with it. It has only something to do with it if you define the unit system you use.
Yes.
And make numerical values upfront. But this upfront definition I have not seen in your ideas, so I cannot really judge how that relates to each other. This is my problem.
Yeah, thank you, Christian. Yeah, thank you, Christian, for clarification. What I meant is, I'm just jumping steps. I'm sorry. What I'm saying is, initially, you look at what we know. Like you mentioned, I agree with you about constants. We cannot crunch out constants in the first step. We are not doing that. We cannot do that. We are just looking at the charge, for example, is -1. That's all we can see. So if the gravity here, the same, I know that it has to be the same level, then we have to put it as 0, because the small value, like you said, we cannot put that because we are not taking into account the constants here. I agree with that. So thank you for your clarification. So initially we will put it as 0 because the logic, we are looking at the logic or the logic component of it, like it's a -12, but we don't know we are not putting the actual value of the charge there yet. So in the first step, we are not doing that. We are just putting, so it simplifies that. We have to get an idea of this, what the matrix can do. We just put -12. So it's just a first step, very first step. We don't put the value of the charge, whatever, 10 to the -19, something coulombs, whatever. We don't put that inside the first step. The first step, we are just filling in what we know about a charge. Charge is -1. So it's unitarized value. So I agree that we have to do unitarization and normalization. That's the step we have to go through. But we can put in the value of -1 for gravity. We know of no particular logical thing for electron that it has separate gravity component like the spin. So we cannot put that value here. So initially we put that 0. Then you have come to the strong nuclear. It's not strong nuclear. Again, that's 0. So we get a very highly reduced matrix. So weak nuclear, yes. So we can put some value here like -1 or +1, whatever we know. So that's all we can do. And dark matter, we don't know whether the electron exists in the dark matter. Okay, so this one simplifies to a very simple 2x2 matrix. It collapses to a 2x2 matrix like the Pauli matrix. Now, I am expecting that it becomes very similar to a Pauli matrix when you talk about electron, except the switch states. So it extends only the switch state. The electron is there. The electron is there, either participating, which means if the electron is there, it's participating or not participating, right? So then it has a value. Like I said, the off, if it is off, then we can substitute that value. And then say if it is not participating, let's say off equal to 0 to start with. So if it's not participating or if it is off state, we put it as 0. If it is on, if the electron is highly active, is the active component, we put it as 1. So we can put that value for the switch states. That's the only difference. For the electron right now, the only difference from the Pauli matrix is that we add one more component called the switch aspect. The switch aspect says whether the electron is on, electron is actively participating or is not there. That's all. So essentially, it will reduce to Pauli matrix in the case of electron if we take out the switch aspects. So essentially the same.
Yeah, but then I don't understand when you say the first line, and I believe to remember you said the first line in this matrix is, for example, the electric charge. The second is, I don't remember, was I think the mass.
Yeah.
The third was the weak. The fourth was the strong. The fifth was the dark matter, and the sixth the dark energy or something like that. You need to quantify at least for dark energy and dark matter, because dark matter and dark energy is not a physical guarantee in our world.
Yeah.
So these are concepts which were invented by other physicists to compensate for their measurement defects, to put it mildly. Let's allow them to say they measured wrong or they have a theory which doesn't fit. So they invented these things to make rotational parameters of galaxies have the right strength or relative to the mass of the assumed black hole inside such a galaxies in this and that distance, so that they don't get things which do not fit to each other from a theoretical point to a very high degree. so to about say 6-7 digits of precision. Now, when you have just the awareness, the on or off of these things, then you cannot actually say anything about the consistence of dark matter or the consistence of so you can apply the calculation for a theoretical purpose, which I don't fully understand. This is fair enough, but as a scientist, I want to find out things, and I want to calculate things which I later can, in ideal case, find in the universe and measure and compare to what you calculate. So to what exactly, measurement-wise, would you compare these results you calculate to?
Okay. So one of the things I will do, ago I only finalize this one. So this is just initial stuff, the logic aspect. Now I will try to work out, for example, I'll try to work out a problem for the electron, for the positrons, and how it will look like, you know, so how this matrix, the numbers will come up with. So that's one thing. And thank you, Christian, for pointing that out, because that's something, you know, I'll try to do. The next step is to find, for example, examples, for example, electron and positron, which are similar thing, and how the values come and how they compare with the Pauli matrix, for example. That's maybe a one immediate step I can do. It may take a few days. I don't know whether I can, you know, hopefully by next presentation, I can probably pull out some examples. So if I put examples with the values there, and for example, the on-off switch is one of the things that interesting. Again, it will take some time to understand. But I feel confident that, for example, dark matter, the electron may not be participating. So it may be off, or we have to put it as 0. The electron as such may not be the electron that we know of in the mesoscopic or the quantum level that we measure as, you know, as being there. It has a charge and is actively doing the
wait a second, you're saying 0 means it's not there, but if it's not there, then does that not mean it does not exist?
No. In the first step, we are saying that 0 means either it is not there or it is off. It may be there, but it's not participating. To start with.
Oh, I thought off meant that it wasn't participating.
Yeah. Eventually,
0 means that it's just not there.
Yeah. Eventually, that will make the differentiation later on. So this matrix does consider that, but that's much later. So the thing is the initial.
Yeah, I don't know, but that worries me though. That everything is like you say I don't know. I'll know later.
We don't know. The dark matter.
I accept that. I mean, that's something. That's like what I'm doing. I'm kind of like working away, and then hopefully something comes out of it at the end.
Yeah.
So it's like a formalism kind of thing. It's like a game that I'm playing. It depends. Like I have different research that like can be disproven straight away once the results are there.
Yeah.
I just have to do them. But then the stuff I'm currently working on, you just need to step through it, see if it's doable, and it might have something good at the end. It might not. So I respect that. But
Rajan,
just one last point, Christian. But see, my worry is that there's just like with math, it's like an infinite number of variables of things that you can link together and stuff, and so it worries me that if you've no like structured path, you're just kind of going into the void and grabbing hold of things and hoping that you know what I mean. So I'd be a bit worried about that if you don't exactly know where you're going and what you're like. Maybe you don't know what the results are going to be. Fair enough, but at least you know when you get there that you finished the road or something. That would be my worry.
Yeah, it's an excellent point. Like you mentioned, you know, one of the things that got me engaged was you did your crystal and you were able to get some connection to the bosons. You are able to put in some values there. From your pure game-like thing, you came up with the 24 cell, your 600 cells.
Yeah, no, actually, well, that exists already. The 24 cell. I suppose I suppose I have a strange take on it, but not really, because it's related to other people's work. But I would say that their work is kind of closer to yours in the sense that you have this 6 what is it, a vector with 6 elements in it or something, and each one is some sort of
one.
Yeah, exactly. So this is that is like
This
something
one, right?
that's used a lot in physics. So that's, you know, so there's definitely something there. But yeah, it's interesting from that point of view. It's not totally in space. It could be.
Yeah.
Roger and Christopher, if you allow my, I need to leave soon. The 2 hours are nearly over.
Yes.
Or they are over and a little bit over time. But what I wanted to state is the following. At a very long meeting ago, I brought up a point that literally 10, 15 years ago, and I couldn't find it yet, but at least I'm sitting on the right machine. You might have noticed that I'm on BHI book 6 today, not 7. I managed to repair that machine back, and now I have access to the data on BHI book 6 again. And there were a lot of iSpace and physical calculations I did in the last 20 years, which were not on the copy of this BHI book 7, which I had participated with in the text meeting so far. And the historical reason for that was as simple as it is stupid. The initial space memory of that BHI book 7 had only 256 gigabytes of flash, and the original machine had 2 terabytes of flash. And so I was essentially lacking 80% of my own data and my own equations. So of course I had hoped to copy the most of it, but it was really a rough emergency copy after that old machine died off, and this very 14-year-old machine, which I recovered. So, but that is not the important point. The important point is one of the things which I talked about was a paper which was crisp, clear mathematically, and which opened my eyes to tensor mathematics and abstraction in general. So why do people abstract? And IT people do abstract to save time to type or to talk. So you can go to your boss and say, let's have that Qt library XYZ do KLM. Yeah, then a lot of people in the room will say, whatever, yeah, XYZ KLM. But 2 or 3 people in the room will say, yeah, let's exactly do that. That is a good idea. Everybody else said, if you think so, yeah. And from the 10 people in the room, only 2 or 3 knew what they were talking about, and the other 7 never heard about that, because it might be a VARC area of a library with 35,000 possible entry points, which you normally need 20, and from the other 35,000 you have never heard. So when you are an informatical guy, you should get things very precise, or it pays back later hard. When you run your program, it will crash at runtime, because you didn't think in compile time what you wanted to do when you not properly define your things. And this paper, which I'm debting you, because I said I wanted to search for it and give it to you, was written by a German mathematician when I was still studying physics. And it opened my eyes during the study, because I couldn't understand what the professor was writing on the wall. Really, it became ever more complex, and I was good in IT, and I was not really good at physics, not at all. So they quickly hooked me off, and they didn't hook me off by the physics, interestingly. They hooked me off by the math. I couldn't understand what they were talking about, because I couldn't do the simple integration equations which they showed and so on. And that quickly began to be matrices and matrices of matrices, which are tensors. And as I said, I happened to code Mathematica tensors in the past, because I needed to give parameters to the Mathematica kernel in tensor form. And hence you have to deal bit by bit in detail where the hell the things are which you want to give to the Mathematica kernel from the user interface. So then you understand the hard way, because that, hey, that with all of these tensors is not so complicated, because it's just matrices of matrices of matrices. And someone has to define, human-wise, do we give the column first? Do we give the row first? Do we compress zeros? Do we give the full thing? Do we allocate multidimensional? The tensor can have any rank. So you can have a 10-dimensional tensor gives a terabyte of data as a function call. And then the function which gets called IT-wise needs to sort out what the hell the caller had intended. So when you're a CUDA library, your user might want to do something very simple, but he might use Python in a special version. And that specific version of Python might have big endian memory. And that means that your high byte comes before your low byte, and certain things mean only something to you when you know the big picture. So when you go onto the bit level and really look what has been defined, is not otherwise anything special with that. But that makes it complex for 99.9% of all people looking at the code, because they see a hard load of copying code, DMA controller selection to make things faster. And all it is about to copy data from function A to function B in a function call. And a synchronous one, this is actually a trivial thing in IT, but it looks horribly complex when you look in the interface code, because it is horribly complex because of the number of abilities your matrix definition can go. And to understand that kind of matrix definition, this German mathematician, which I told you, has made a loop unroll of all of that, what the symbols mean in these integration equations. So that when there is an integral sign, and when there is a bracket, and when there is, what does it mean? Yeah. And he made it in a way that I could understand it. And I said, wow, that is simple. So what I wanted to do is to give you this paper, which made me understand why is that actually completely simple after knowing it, that they just wanted to do this and this and this, but exactly. So the programmer brain needed something nailed on the wall, which cannot change anymore. And that helped me to get things. And I wanted to give you both that paper. And the hard thing I ask for is give a singular example for one future text, could be month in the future, doesn't matter, nothing urgent, where you loop unroll one of your things, even the first bracket of the bracket of the bracket, and make it explicit. I said, what would that mean in Mathematica in detail? When you would code it, what would be written there? And without any abstraction, where it's just core language, and like you could read bracket open, then a number, a comma, whatever, yeah? Because once you code that thing, you need to be precise. You cannot take verbal action anymore to say this is this or that. You have to be sure that I mean a 1 here, I mean a 0 here, I mean a bracket open here, I mean whatever, yeah? But no symbols in its own, no library function, which makes life easier. Just plus, minus, multiplication, and what is multiplied with what. In a normal matrix, when you have a 2x2 matrix, then you don't see it easily, but with a 3x3 matrix, you see it easily. You multiply the left upper with the left center, then you multiply the left center with the right upper, and then you would multiply right with nothing, because nothing is on the right side, then the matrix wraps to the left side, and you multiply it with one row down with the next row on the left side. Or it's just a shell game.
Yeah.
And when the matrix gets bigger, the shell game is not easy for humans to check anymore. But a computer has an easy time to say, yeah, of course we do that, because it's just formalism. Yeah. But that formalism is in your way when you want to talk about physics. This is what I learned from the true physicists, which I had get contact with, like my physics teachers. And they said we need that formalism to talk to each other in a fast way, like you need your formalisms and IT to give libraries to your colleagues or to your whatever the rest of the world when you program something that they know how they call it. And I think we need to find a more common language before discussing these kind of things publicly. Yeah, think of that. We're doing that publicly here. And when you publicly state something, it should be for everyone have not ever heard about Rajan Ear or Christopher or me, doesn't know anything about iSpace. It should be clear by following the 1 hour from your presentation. This is what Rajan means. Yeah.
Yeah.
It shouldn't be the way that you needed to have seen the last 100 text meetings to get an idea what you're talking about.
Yeah. Yeah, I agree with you, Christian. This is such a new thing that only a few days ago, I just want to start doing that, and then what I call think aloud about this one. What you mentioned is true. Like I had to have a value here. That's what I will try to do, find examples and put value. For example, what happens with the electron. So this will have a numerical value. I'll put a numerical value, and then you multiply this, by the first one, and then add this. Multiply these.
We don't need to do that now. That I need to leave now. So it was just the suggestion which I have to you. Of course, you can free with your time to go for what. But I will really now search for that paper and mail that paper to you as soon as possible. That you see the difference between the compacted form, the physical form, and the loop unrolled form of where you easily see that there is nothing much behind all that mathematical formalism. But it's on 2 A4 pages, and it was really stunning for me. And once you have that paper, you will understand what I think should be the prerequisite to these kind of discussions, because that should be easy for everyone. I always try to do ice-space theory in a way that everybody can follow, let alone have studied, not studied. It was about, of course, not for beginners, but say 10th grade of school should be enough. They have learned about what integration summation is, and they have learned about what a little bit IT stuff is, and that should be enough to follow. And probably it is, because we're doing just multiplication in iSpace. But this is not just multiplication. On the other hand, it's not much more. It's matrix multiplication and matrix multiplication and matrix multiplication. And so it's a little bit logarithm, it's a little bit exponential, it's Lagrange, but Lagrange has a mathematical formalism which you can unroll if you want. And then each of the operations of each of these symbols, very dense, could be written in a, say, 10,000 line source code program, which then makes it completely clear, or on a chalkboard with for the first equation with chalk on the whiteboard, unrolling what it would mean if it would not be shortcutted. And then at least we would have a common basis to talk about that, because it is really hard to grasp shortcuts while the left end of my brain hears the words and the right end of my brain tries to sort them into some binary bits and bytes to understand what they mean. And this is not possible for me, at least not in real time. So this is very hard to follow. This is what I can say. So thank you for your understanding.
Thank you. Yeah, I'll try to make an example. Next time when we meet, I will put numbers there, because you have to eventually put numbers and then and calculate by hand calculation, because computer is only
find a way to agree on that, because there's surely something behind, and we need to just understand what each of the symbols on a specific super shortcutted example would come out from left to right in full detail.
Yes.
You can even email that to us, Raja.
Yeah. Let me. It might take a little while. I don't know. Are we having next week?
Okay. We're not going to meet next week or anything. So 2 weeks should be.
There's nothing urgent in the sense that take your time, and I will also find a way to find out that paper. And I thank you for your time and understanding, and have a nice further evening. Okay.
You too.
Thanks a lot. Thank you. Have a nice evening.
Bye. Thank you.
Thank you. We'll see you next time.
Yeah.